Come back. Negating quantified expressions. What is the negation of all children like chocolates? Well, negation of this proposition is there exists a child who does not like chocolates. So, use logical arguments to prove the following logical equivalence. Negation of for all x such that px is equivalent to there exists x such that not px. Prove the following logical equivalence. Negation of there exists x such that qx is equivalent to for all x negation of qx. We have the De Morgan's laws for quantifiers. Negation of there exists x px is for all x negation of px. When is this negation true? For every x, px is false. That's what negation means, right? When is this negation false? There is an x for which px is true. Likewise, negation of for all x px such that px, this is actually equivalent to there exists an x such that negation of px or not px. So when is this negation true? There is an x for which px is false. When is this negation false? Px is true for every x. Think about the following exercises. These are just bunch of exercises. What is the negation of? There exists a perfect airline. What is the negation of? Everyone likes a good dance. What is the negation of? For all x, square root x less than x. What is the negation of? There exists x such that cube root x greater than x. Show that negation of for all x, px implies qx, and there exists x such that px and not qx are logically equivalent. Express the statement. There is a student here who walks to school using predicates and quantifiers. Express the statement. Every person here has seen the Statue of Liberty using predicates and quantifiers. Express the statement. Some person here has never gone on an airplane using predicates and quantifiers. So you see, these are all short exercises for you to try. If something is unclear, reach out to me, okay? Using quantifiers in system specifications. Use predicates and quantifiers to express the system specifications. Everyone taller than 6 feet will sit at the back. Use predicates and quantifiers to express the system specifications. If someone needs help, an office hour will be held. Let px, qx, and rx be the statements. X is a clear explanation. X is satisfactory. X is an excuse, respectively. So, X is a clear explanation is px. Qx is X is satisfactory. Rx is X is an excuse. Suppose that the domain for X consists of all English text. So that's your domain, all of the English text. Express each of these statements using quantifiers, logical connectives, and px, qx, and rx. All clear explanations are satisfactory. So you would say, for every x, px implies qx. That's what this means. Some excuses are unsatisfactory. There exists x such that not qx. That's what is B. So, try C and D yourselves. Logical programming. Prologue. Programming in logic. Developed in 1970s by computer scientists working in the area of artificial intelligence is an example of a language designed to reason using rules of predicate logic. So that's prologue, as in programming in logic. Prologue programs include a set of declarations consisting of two types of statements: prologue facts and prologue rules. Prologue facts define predicates by specifying the elements that satisfy these predicates. So that is, facts define predicates by specifying elements. Rules, prologue rules, are used to define new predicates using those already defined by prologue facts. Here is an example to understand what we just said. Consider a prologue program given facts telling it the instructor of each class and in which classes students are enrolled. The program uses these facts to answer queries concerning the professors who teach particular students. Such a program could use the predicates instructor of P, C, and enrolled SC to represent Professor P is the instructor of course C. Student S is enrolled in course C. For example, prologue facts might be instructor Chan, Math 273. What does this mean? Chan is the instructor of the course 273. Instructor Patel, EE 222. Instructor Grossman, CS 301. Enrolled. So these are instructors of their respective courses. Enrolled. So Kevin is enrolled in Math 273. Juana is enrolled in Electrical Engineering 222, and so on. So notice a student could be enrolled in more than one course. Okay. Lowercase letters have been used for entries because prologue considers names beginning with an uppercase to be variables. So this particular programming language uses uppercase letters for variables. A new predicate teaches PS representing that Professor P teaches student S. So you see, professor to class, students to class. Here we are talking about professor to a student, teaches PS, right? The rule is teaches PS is given when instructor P to a class is given and student S to the same class is given. So teaches PS is true if there exists a class C such that Professor P is the instructor of the class C and the student is enrolled in that same class. Comma is used to represent conjunction. So that's what. You want this instructor to teach the class and the student to be enrolled in the class. So comma here should represent conjunction, that is and. A semicolon is used to represent disjunction. Okay, so in this statement we didn't need a disjunction, so we did not have a semicolon. Prologue answers queries using the facts and rules it's given. For example, using the facts and rules listed, the query question enrolled Kevin Math 273 produces response yes. Is Kevin in Math 273? That's the question. Response is yes. The query enrolled X in Math 273, that's a query, that is question. What is X? So who is enrolled in Math 273? Go back and check. Math 273 has Kevin and Kiko. So you should get these. To produce this response, Prolog determines all possible values of x for which enrolled x mat 273 has been included. Similarly, to find all professors who are instructors in classes, we may use query teaches x Juana. So who is teaching Juana? Juana is in EE222 and CS301. So EE222, Patel is the instructor, and CS301, Grossman is the instructor. So you should get Patel and Grossman. Alright, so this is an example of a program, okay, of a Prolog, that is programming in logic. This completes lesson 4. Next video will start with lesson 5.